All right, welcome back to Math 1324. We are starting with a new chapter. Chapter 7 is called Logic, Sets, and Counting. And the first section we're going to talk about is over sets. So some properties and notation. Definitions first. A set is any collection of objects specified in a way that we can tell whether any given object is or is not in the collection. Some notation of a set. Sets are often denoted with capital letters. So an example, we might say that set A consists of the lowercase letters A, B, and D. And we could say that set B consists of the letters B and C. So those are some notations. We denote the set with a capital letter. Okay, each object in a set is called an element of the set. So in our example set A, we have three elements. We have little a, little b, and little d. Those are all elements. The elements are often denoted with a lowercase letter. And some notation. Little a is an element of A. That symbol here, that symbol means it's an element. You can also say not an element of. So in our example, we could say that C, little c, is not an element of our capital set A. Letter C is not an element of our set A. Okay, a set without any elements is called the empty set. So we could denote set C, we can say either it's the empty set. Sometimes you'll see it written like this. It's a set with nothing in it. Okay, the empty set is denoted by, that's the empty set. We represent a set by listing all of its elements between braces or by enclosing a rule within the braces that determines the elements of the set. For example, we could let set A be Saturday and Sunday. That's one way to denote a set. You can list the elements. Or you could say set A is all the elements X, where X is a weekend day. Two different ways to denote a set. You can list the elements or you can define it by a rule. All right, a finite set means that the elements can be counted. There is an end to the number of elements. For example, our set A that consists of the elements -2 and 2, that is a finite set. There are 2 elements in that set. Whereas an infinite set has no end when counting the elements. If we define the set A to be the even integers starting with 2, so 2, 4, 6, 8, 10, 12, that is an infinite set. We cannot count all of those elements. Okay, a note. We do not list an element in a set more than once. If it's in there, it's in there. Also, the order in which the elements are listed does not matter. If you wanted to be really weird and say that this is the set 4, 8, 2, 6, 16, okay, we can't tell that there's a pattern, but it does not matter what order the elements are listed in. That's actually a bad example. If I were to go up here, I could say that this is the same as the set 2, -2. That's a better example. If you have a finite set, it does not matter what order you list the elements in. All right, keep going with definitions. If each element in a set A is also an element of set B, we say that set A is a subset of set B. And the notation looks like that. A is a subset of B. An example, if we knew set A was the elements A and B, and we know that set B consists of the elements A, B, and C, then we can say set A is a subset of set B. Okay, but we cannot say, we say that B is not a subset of A because B has the element C that's not in A. So to be a subset, every element here has to be an element in here for it to be a subset. All right, we say that two sets are equal if they have exactly the same elements. So let's go over here. If set A had the elements 1 and 2, and set B also had the elements 1 and 2, notice that I said them in a different order, but that's okay. It's still the same set. We can say that sets A and B are equal. Okay, and note, if A is a subset of B and B is a subset of A, then they have to be equal. Some other important things. The empty set is a subset of every set. So no matter what set you're talking about, the empty set is a subset. Also, every set is a subset of itself. So A is a subset of A. All right, let's get into some examples. Given that A is the elements 0, 2, 4, 6, B is the set 0, 1, 2, 3, 4, 5, 6, and C is the set 2, 6, 0, 4. Indicate whether the following relationships are true or false. For this first one, is A a subset of B? Everything in A has to be in B as well. So is 0 in B? Yes. Is 2 in B? Yes. Is 4 in B? Yes. Is 6 in B? Yes. So that is a true statement. A is a subset of B. Is A subset of C? 0 is in A, 0 is in C. 2 is in A, 2 is in C. 4 is in A, 4 is in C. 6 is in A, 6 is in C. So yes, A is a subset of C. Now the next question says, is A equal to C? They have exactly the same elements. So yes, they are equal. D. Is it true that B is not a subset of A? So can you find an element in B that's not in A? 1 is in B and it's not in A, so B cannot be a subset of A. That is a true statement. Is C a subset of B? Okay, since A was equal to C and A was a subset of B, then C is going to be a subset of B. That is true as well. If you want to go check that one out, 2 is over in B, 0 is in B, 6 is in B, and 4 is in B. So everything in C is also in B, so we say that C is a subset of B. Is the empty set a subset of B? Remember that the empty set is a subset of every set, so this is a true statement. Okay, list all the subsets of A if A is the set 1, 2, 3. Okay, the subsets. The empty set, the set that contains just 1, the set that contains just 2, the set that contains just 3, the set that contains 1 and 2, the set that contains 1 and 3, the set that contains 2 and 3, and one more, the set that contains 1, 2, and 3. Those are all subsets of A. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 subsets. Okay, are the following true or false? Is the empty set a subset of the empty set? Yes, that is true, because the empty set is a subset of every set. Is the empty set the subset of the set just 0? Yes, that's a true statement, because the empty set is a subset of every set. All right, now let's get to Venn diagrams. I love these things. Okay, a Venn diagram is a picture that helps to visualize the relationship among sets. Okay, before we get started, U is called the universal set. It's everything that we're considering. So U is kind of like that rectangle. It's the set of all elements under consideration. Okay, the union. Notice some verbiage, some definitions. A union B. Union can be thought of as or. It's in A or it's in B. So it's the set of all elements X, such that X is an element of A or X is an element of B. I also think of it this way. Everything from A gets put into the cup. Everything from B gets put into the cup. Union. All of A, all of B. So the union is everything that's shaded there in brown. All right. The intersection, A intersect B, it's all the elements that are in A and that are in B. They have to be in both. So I think of it this way. You remember how the union, we dumped everything in? When you turn it upside down and make it into an intersection, only the stuff that's in common sticks inside the cup. So only the stuff that's in common stays in there. Why is it not letting me write? Hold on.